Alright, this is Schweitzer, and we're making our way through this tutorial on acids and bases. And the topic here is what's left. We know when we mix acids and bases that we neutralize, and what's left afterwards determines the pH or the acidicness or the basicness. So if I mix an acid and a base together, I have my initial amounts, my stoichiometric ratio, my end. The ending point really is what determines the ending pH. I mean, would make sense, correct? You should be aware that when you mix an acid and base together, you get a salt and you get water. The acid, its conjugate is basic, and that's part of the salt. That's the anion, the cation. Let's do it like this way. Let's call it the cation and the anion. That's a weak base, and then the base, its conjugate's the cation, which would be a conjugate acid. So just so you know, the salt can definitely be acidic or basic in the end too. Either way, with that information, you should note that if you only have salt left over and these two things cancel evenly or neutralize evenly, are you guaranteed to be neutral? No. Only if your salt is neutral. Now that's a topic that in honors chemistry we kind of skim over or do not even talk about at all. The pH of a salt. We would assume that if your acid and base are gone, then the products would be neutral, and therefore you would be neutral. And for the most part of our calculations here, we're just sort of tiptoeing into this, would be okay. All right. So here is a basic question. What if we have 100 milliliters of 0.1 molar HCl, and I am mixing that with 50 milliliters of 0.2 molar NaOH. The first thing you should realize is that we have HCl plus NaOH will yield NaCl plus water. Initial amount, stoichiometric ratio N. I want this to be in moles. Before I do all the math, I might note, just do some proportional math and say, okay, well, what if I have 100 milliliters, okay, of 0.1, and I have half the concentration of this, half the volume, but I have twice the concentration. You should be able to do the math in your head to realize that, okay, at this point, I have equal moles, and therefore they'll cancel at equal rates, at 1-to-1 rate, and therefore my pH would be 7 in the end. So let's go ahead and do the math in this first. I have molarity equals moles per liter. The molarity is 0.1 on this guy, and I get 0.1 liters. Solve for the moles. The moles in this case equals 0.01 moles. And the 0.0 moles is this guy, 0.1. This one, 0.2 equals, and you should get the same answer, X equals 0.01. 0.01. So at 1 in ratios, they both knock each other out at equal rates. And I have nothing left, and that for this purpose, we're going to say pH 7, and it is actually 7 because this salt happens to be neutral. I would gain 0.01 of this, and I would gain 0.01 of this. Now, I can divide this by my new volume, which is now 150 milliliters, or 0.015. Water, technically I can't divide by the volume because I wouldn't divide up moles of water by by volume of water. It doesn't work that way because it's all water. So you do not have a concentration of water. This guy here, 0.01 divided by 0.015, and we're getting 0.66 moles per liter. That would be the concentration of my salt. Typical question that could be asked here. pH is 7, and my salt is 0.66. Okay. All right. Next question. Let's say we have let's go with 0.5 molar of 25 milliliters, and let's say I got let's say Cl. Let's go with, again, I'm using a strong, doesn't matter which one I use. Let's use a different one. Let's use HNO3, and let's go 0.2 of 50, 0.2 molar. Let's go with 50 milliliters of KOH, again, strong base. HNO3 plus KOH yields KNO3 plus H2O. At this point, I have some different volumes, 25 and 50, double the volume, but it's not half the concentration, it's less than half. So this should be my limiting reactant. Initial stoichiometric ratio end, let's do 0.5 equals 0.025 over x, half of that, x equals 0.0125, 0.0125, and then this guy is 0.2 molar equals 0.05 liters x, and 0.2 is 1/5, and 1/5 of 5 is 1, so this is going to be 0.001, 0.001. Again, use at 1-to-1 ratios. My proportions mentioned this would be slightly less, and therefore minus 0.001 to 0, minus 0.001 leaves me left over just so you're aware, one small error there, fix that quickly before it gets too far, 0.01, so I have 0.0125 minus 0.01, this is just going to be a leftover of 0.0025. Now, I have acid in excess, therefore, that's going to be what's going to determine my pH. This guy happens to be a neutral salt here, and in this case, you take, I'm still going to get 0.001 plus 0.001 divided by the new volumes, that would be 50 and 25, that's 75 milliliters, 0.075, and I get, in this case, and be 0.01, not 0.001, 0.01 divided by 0.075, and I get 0.13 molarity of my salt. And then this guy is going to be, well, I still have 0.0025 left, divided by the 0.075, means I have 0.033 molar left. Negative log of that previous answer is a 1.4 molar concentration left. Doesn't seem like it should be bigger than 1. Maybe I made a math error there. No, I didn't. Hold on a second. Oh yeah, pH is 1.4. That's the thing. pH is 1.4. All right. That's your typical question, how that works. Now let's try another example. Okay. All right. Let's take 0.5 molar, let's say 25 milliliters of HF, all right, and let's say I got 30 milliliters of 0.1 molar, that'll work, NaOH. Now, all along the way here, we would be drawing pictures of these things. So the first one, let's take a break on that one for a second. What's the end picture look like? The end picture looks like essentially just the end. I have no stuff left. We might even draw initial pictures too. So the initial pictures would be the same amount of these guys. Essentially would have, let's say, let's just go with 2 of them. H plus, Cl minus, and Na plus, OH minus. You might have them in separate beakers, but these two guys will react to form a water molecule, and the Na plus and Cl minus are floating around. All done. The next option here would be, let's draw the middle one here. I would have excess. So let's do this thing here. I got the HNO3. I'm going to call it HX. That's this guy. And then the KOH, we'll draw that guy. And then the ending beaker, what's it look like? Well, I know I have excess HNO3, so I'm going to draw 1, 2, and 3. Squeeze a third one in there. And here I'm going to have 1, 2, 2 of them, and K plus and K plus. So to pour them together, these two guys react, these two guys react, and what's left over? I have an H plus left over, so the H plus will still be there. I have two waters, which I'm not going to, well, I could put the water in, H2O, H2O, and I have two cations that are not used, and I have two anions that are not being used. And there we go. Probably could have drawn a bigger picture. Draw a bigger picture of the next one. Alright, so next guy here, we have HF. Now, this is a weak acid, but again, it doesn't matter. Your total moles is all that matters. The fact that it's strong or weak really does not affect the neutralization. Alright, so in this point, I have 25 milliliters of 0.5, and I have 30 milliliters of 0.1. You should note that this is many times more concentrated, and I have almost the same amount, so the acid will be in excess. Anyway, we'll run out first. So HF plus NaOH yields NaF plus H2O. Alright, so in this case, let's do the math here. I have 0.2, 0.5 equals 0.025 liters over x moles. X equals 0.0125. 0.0125. This guy is 0.1 equals 0.03 liters. Solve for x. X equals 0.003 moles. 0.003 moles. So I have quite a bit less of it. In this case, I would have initial stoichiometric ratio end minus 0.003. Minus 0.003 goes to 0. And this guy is going to be again, now we're getting a salt and we're getting a water. Keep in mind, this is a weak acid, so this conjugate is a weak base. So technically, as we move forward in chemistry, you would note that that conjugate is a weak base. At this point, it doesn't really matter. All I know is I have some weak acid left, I have some weak base left. For this situation, divide by the new volume, which is, in this case, 30 plus 25 is 55 milliliters, 0.055 liters, 0.055 liters, and I get my new concentration. Alright, 0.003 divided by 0.055, and I get 0.054 molarity of that guy, and I get 0.0095 divided by 0.055, and I get 0.172 moles per liter. So not only is my acid in excess, I didn't even neutralize half of it. So let's take a moment and draw out some beakers of this thing. Okay. Okay, so I have HF. Let's draw a picture of HF. Draw a picture of NaOH. Computer's slowing down a little bit here. Yields and then the overall beaker picture. First guy, I have HF, and in the quantities just need to be in excess, so I'm going to go 1, 2, 3, 4, let's go 5 of them. And usually I would probably take a moment and make sure my volumes are somewhat close to what we got here, but in this case it doesn't really matter. Okay, and then I have NaOH, Na plus, OH negative, and I might just do one of them. Note that I have I'm trying to mimic my number of moles. Now at this point, hydroxide can react with one HF to flip it to water. So I have my formula, even though that's the molecular version, the net ionic is HF plus OH negative yields H2O and F negative. One of my bases can react with one of my acids to flip it to my products. I'm drawing a bigger beaker because I have more volume in this guy. Alright, the volume's added up. Alright, and at this point I have H2O and I have F negative. That's that conversion. And then at that point, the cation, sodium, is accounted for. And I have 4 HFs that just did not get even talked to. Now, how would I determine the pH of this thing? The pH of this guy, because HF is a weak acid, I would need to use the concentration of 0.172 and the Ka value, which is, for HF, 6.6 e to the negative 4th, and I would use the process for finding the pH of that guy. I would also need to, let's do that, let's just show it quickly here. For honors chemistry, this is not something we generally include, but the way to do it is HF plus H2O yields F negative plus H3O plus, initial stoichiometric ratio, and we do not do this in honors chemistry, but we have the skills to do it. But this guy is 0.172. That's pushing towards the products. Okay, but we have a weak base here, which is pushing back that way. It's a reversible reaction equilibrium, and that concentration is listed as right here, 0.054 and 0.054, and then I just solve the ice table out. Looking for X, not playing a role. 0 minus X plus X plus X, 0.172 minus X, 0.054 plus X, and X. The Ka value is 6. Now I'm going to go, just write it out, 6.6 e to the negative 4th equals the concentration of my products, F negative, which is NaF, by the way, and he's a spectator, H3O plus, and then the concentration of HF, and water is not included because it's a pure liquid. 6.6 e to the negative 4th equals, top, I get X, and then rather than having that X value there, I get 0.054 minus X, and then I get 0.172 minus X. I would use my shortcut rule twice to eliminate this guy and to eliminate this guy, and then I would solve for X. X, so I got to multiply up, divide below, get X, and then X is the concentration of H plus ions. Times 0.172 divided by 0.054, and I get 0.0021 negative log of that answer, and I get a pH that is 2.67. All right, lots of examples there, lots of pictures. A little bit extreme here. If you are, that's the next video. Actually, is the very next video right there. So we'll do another example of that in that video. Otherwise, notice it's labeled AP, so this is where it'll stop for honors chemistry. Thank you very much.